A mathematical series or summation is shown here in the form of 2 times 2 factorial plus 3 times 3 factorial plus 4 times 4 factorial up to n times n factorial. We want to solve this and show that there is actually a closed form solution for this in the form of n plus 1 factorial minus 2. So very simple, nice closed form. That's interesting, and I'm going to prove this using once a quick direct method and the other one using mathematical induction, and then we can compare these two. If you're interested only in mathematical induction, you can jump to almost the end of this video to watch the mathematical induction only. So in the direct proof method, very quickly, I can write 2 as 3 minus 1 times 2 factorial plus, for 3 I can write 4 minus 1 times 3 factorial plus, for 4 I can do 5 minus 1 times 4 factorial, and I can keep doing this. And for n minus 1 times n minus 1 factorial, naturally I can write n times n minus 1 factorial, which is n factorial, and then minus, of course, just n minus 1 factorial. And lastly, for the final component, instead of n times n factorial, I can write it as n plus 1 times n factorial and then minus n factorial. It's as if I write n as n plus 1 minus 1. Okay, so what's the benefit of writing it this way? Well, let's multiply. So just 3 times 2 factorial gives us 3 factorial minus 2 factorial. 4 times 3 factorial gives us 4 factorial minus 3 factorial. 5 times 4 giving us 5 factorial minus 4 factorial, and keep the rest, so dot dot dot, that's the ellipsis, n factorial minus n minus 1 factorial, finally n plus 1 factorial minus n factorial. So now we can see what's going on. This 3 factorial cancel out with this one, 4 factorial with minus 4 factorial, 5 factorial with minus 5 factorial, and you can see if we keep doing this, n factorial is cancelled out with minus n minus 1 factorial, and there is n plus n minus 1 factorial here that will cancel out this one. So what remains at the end of all this process is just n plus 1 factorial and minus 2 factorial, which is the minus 2. So the outcome is simply n plus 1 factorial minus 2. So that's the direct proof method. Let's do now, so that's method 1. So the second method, is mathematical induction. And mathematical induction is like the domino. So if I can show that I can drop the first, let's say, component, then if I can show that the kth component can be dropped as well, then k plus 1 component is dropped, then we are there. So I'm going to do mathematical induction. And for mathematical induction, it is as if I say, so 1, base is a step. For base is a step, we have to show that this whole statement that 2 times 2 factorial plus 3 times 3 factorial up to n times n factorial is equal to n plus 1 factorial times times minus 2. We want to show that it is correct, and to do that we start with the base is a step, which states that we start with n equal to 2. So in this problem, the first term is 2 factorial. So we are starting with n equal to 2. So basis point is, or b is equal to 2, the starting point. So we need to show that if the statement shown here, if we refer to this statement as predicate p of n, which says left hand side is equal to right hand side, I need to show that p of n equal to 2 is true. So is it true? So to check that, the left hand side is the busy side, the one that is stating this summation or math series. So when we are just limiting ourselves to n equal to 2, as a result, only the first component remains. So as a result, in the left hand side of the mathematical of the expression, we have 2 times 2 factorial. Then on the right hand side, we have 2 plus 1 factorial minus 2. So that is the right hand side. So let's check if these two are the same. So 2 times 2 factorial obviously is 4. 2 plus 1 factorial is 3 factorial, which is 3 times 2 times 1, which is 6. So this one is 6, and then we have minus 2, which is 4. So we have a match. So these two guys are obviously equal. Therefore, the basis step is checked. So that one is okay. Now we need to do inductive step. So in the inductive step of mathematical induction, so this is the second method I am doing. So in the inductive inductive step, what are we saying? We are saying that for any integer k, if k is let's say an integer, so k belongs to set of positive integers, and k greater than or equal to, because the basis step is 2, the smallest value that we can assume is 2, then assume that the left hand side equal to right hand side for k, then prove that the left hand side is equal to right hand side for k plus 1. That is what the mathematical induction is saying. So we're going to assume this is correct, and I'm going to write it. That is basically saying, so I am going to write the meaning of p of k, which says 2 times 2 factorial plus 3 times 3 factorial plus up to k times k factorial is going to be equal to k plus 1 factorial minus 2. We make the assumption this is true, this is correct. We're going to use this. So we assume p of k, which basically this left hand side is equal to this right hand side. That is assumed. We refer to this as inductive or induction hypotheses. So inductive or induction hypotheses. Assumption, basically, our assumption. Now, using this, we want to prove, so now we need to prove that p of k plus 1 is also true, which means, let's write it, so the target now, so the conclusion here, this is a target, or conclusion that we need to arrive at. So in this conclusion, what we have is p of k plus 1 is 2 times 2 factorial plus 3 times 3 factorial, of course, dot dot dot, and then we have k times k factorial and plus k plus 1 times k plus 1 factorial, and that is for the left hand side of the equality. For the right hand side, we need to prove, we don't know, we need to prove that it will be equal to, so we had n plus 1 factorial minus 2. In this case, we are setting n, so let me use a different color so that it's clear. We are using n equal to k. That is our n. So therefore, I'm going to substitute n with k plus 1. So substituting n with k plus 1. Therefore, as a result, my right hand side becomes k plus 2. I'm going to write it here. So let me just put it here. So it becomes k plus 2 factorial minus 2, because I substituted n with k plus 1. There is additional plus 1 here. Okay, so what am I trying to show? Alright, I am trying to now show that the left hand side is equal to right hand side. That's my target. Can I? So to prove that, I'm going to rely on the assumption that we made, the inductive hypothesis assumption, which says this is equal to that. So I'm going to basically up to k times k factorial equal to k plus 1 factorial minus 2. What is that? That is here. So if you look at the target left hand side, the majority of the target left hand side is already the left hand side of the inductive hypothesis, which I can set it equal to this right hand side. So I'm just saying, using inductive hypothesis or assumption, then this portion is simply k plus 1 factorial minus 2, and we're going to keep this as it is. So plus k plus 1 times k plus 1 factorial. So that is our target left hand side. Let's just consolidate that, because we can see that there is a k plus 1 factorial and there is a k plus 1 factorial. So what I can do here is I can just factor out k plus 1 factorial here. So let's see what is the thing I'm gonna get. Alright, so if I factor out k plus 1 factorial, I'm gonna get k plus 1 factorial, and then I'm gonna get k plus 1, which then I'm just trying to evaluate the things I can do. So maybe the best thing to do is, instead of k plus 1, I can write it k plus or I can, this is fine, I can just factor out k plus 1 factorial. So what happens is this k plus 1 remains as it is, and then this k plus 1 factorial becomes just 1, and then we can keep negative 2. So now we are done, because this k plus 1 is k plus 2, so I get k plus 2, and then that is times k plus 1 factorial and minus 2. And of course this is k plus 2 factorial and minus 2, and that is exactly what we needed to arrive at as the target left hand side. So basically we started target right hand side. So we started with the busy left hand side of what we needed to prove. Then for a majority of it we used the inductive hypothesis, that was the assumption we were allowed to make. We substituted the majority of the left hand side using that hypothesis that allowed us to replace it with this component, and then we kept the one remaining element or component, and then we factored out k plus 1 factorial that is common, and then we got to finally the target right hand side. So with this we can say, okay, inductive hypotheses also checked and work. So because we managed to prove both basis step and inductive step, therefore we can say, so because both of them are valid, then we can say because of based on math induction, or based on based on math induction, or using math induction. So using math induction, we can say for all n integers that are positive and also greater or equal to, we can say p of n is true. By p of n meaning that the statement, so what is p of n? P of n is the statement that says 2 times 2 factorial plus 3 times 3 factorial plus dot 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 up to n times n factorial is equal to n plus 1 factorial minus 2. So that is what the meaning of p of n is, and we are saying we just proved that for any positive integer greater or equal to, this statement is correct. Left hand side is equal to right hand side. Alright, so I showed and proved that this summation converges to this closed form formula. So there is a closed form formula in this format for this series or summation, and I proved it using two methods: one quick direct method or direct proof method, and the second one mathematical induction. I hope that this example is helpful in terms of illustrating two proof methods for a summation or math series in which we are using direct method and math induction. Thanks for watching.